Okay, this is a special YouTube lecture for Comp215 about heaps and sorting. Special YouTube lecture because class was canceled yesterday because of the flooding in Houston. So before we go any further, if you were impacted by the flood, if the flood is keeping you from being able to get your project done this week on time, please email me, ask me for an extension. Not going to be a problem. We want to take care of you if we have to. All right. So there are two YouTube videos today. The first video is about heaps and sorting. The second video is going to be about debugging. The URLs for both videos will be posted on Piazza. I'm going to try to get video 1 up today, Friday, and I'm going to try to get video 2 up by Saturday. All right, all the URLs will be posted on Piazza. All right, so first, queues and stacks. So a stack means last in, first out. That sounds very fancy, but it's actually really straightforward. It means that if I put in ABCDE using, say, sequence.prepend, ABCDE, E is going to be in front. And so the last thing I put in was the E. The first thing I take out by asking for the head will be E. So the last one in is the first one out. So your lists and sequences behave like stacks if you just use head and prepend. A queue, on the other hand, which you're implementing this week, is first in, first out. So think of it like a supermarket checkout line. If the people who get in line are A, B, C, D, E, and then the first one out is going to be A. So the first one in was A, the first one out is A. And we can build these in functional or mutating styles. It's actually straightforward to do it either way. How might you implement a mutating queue? Well, you could use a doubly linked list where every node has a pointer to its next and its previous node. You have to do some extra work to deal with the empty list, which I'm not really going to get into today. But when you do it right, it's constant time inserts and constant time removal. Even better, it's constant time for you to add to the front, remove from the end, add to the end, remove from the front, any direction you want. And when you do that, when you can add it to the front or the back, we give it another name. We call it a double-ended queue, or a deck. You can even implement a deck with an array, and we have one that's provided to us in the Java util collections classes called, cleverly enough, array deck. The trick with implementing an array deck is you have to keep track of where the start is and where the end is, and if you grow it too much on one side, it might wrap around to the other side. So you've got a lot of bookkeeping to do to make sure you keep track of the start and the end. And if you fill it up, you have to make yourself a bigger array, which sometimes requires an order n copy, but that cost relative to the cost of all the insertions and removals, not so bad. So an array deck is still going to be, amortized, constant time insert and removal. So far, so good. What about a functional queue? Well, what you're doing this week is using two functional lists, which we are calling inbox and outbox, and it's constant in amortized time. Why amortized? Because sometimes we have to pay a linear cost to reverse the inbox into the outbox. And for an analysis of that and why it's constant amortized time, please read your project handout from this week. That has the analysis. We're not going to talk about it today in lecture. You could imagine doing this with a tree instead. If I had a functional tree, which we'll talk about how we might build one next week, if I had a functional tree, then I could insert and remove the smallest thing, which takes me logarithmic time to search on the left side, or the largest one, which takes me logarithmic time to search on the right side of the tree. We could do it, but we're not going to do it that way because A, we're paying for all this cost of managing the tree, and B, if we have something that's more efficient, if we can do it in constant time, let's go with constant time. But today's lecture isn't about any of that. Today's lecture is about what are called priority queues. A priority queue, once again, can be done in a mutating way or in a functional way. Today's lecture, I will describe a mutating priority queue. Built into Vavr, there is a functional priority queue. So first, let's talk about the mutating one. I've shown you a simple Java interface here on the bottom of your screen. Our mutating priority queue has 4 methods. It has a getMin, which gives us the smallest value and removes it at the same time. I have an insert method, which inserts a new value and returns nothing. And I can ask for the size and ask, is it empty or not? And there's also a constructor, and if I make one, it starts off empty. So far, so good. So that's the interface to a priority queue. Now, I have to have a way of defining ordering for me to have a notion of what's the minimum. But whatever that ordering is, and we'll get to that in a minute, I need a way of getting the smallest one. And then I want to be able to repeatedly call that to get them perhaps in a sorted order. And if you use this, then we could even turn a priority queue into a sorting function. That's actually next week's lab. Inside our priority queue, the implementation is a data structure that we're going to call a binary heap. This is a classic data structure. It's been around for a long time. What a binary heap is it's an efficient implementation of the priority queue interface, of the mutating priority queue interface. The trick is that it's a tree without pointers. So rather than having a node with a left pointer and a right pointer and having to store all those pointers and follow pointers, instead it's just an array. And we're going to map from array indices to different array indices when we want to navigate this funny tree. And the tree has the shape shown on the right, where we fill the rows in. The top row has 1 node, the second row has 2 nodes, the third row has 4 nodes, the row after that would have 8 nodes, etc. And when we fill the nodes in like this, from left to right, from top to bottom, a tree that has this specific shape we call a complete tree. So the blue numbers tell you the index in the array. The yellow numbers are the contents. We'll come back to the contents in a minute, but I want to focus on the navigation for now. To get from node 0 to node 1, I multiply by 2 and add 1. 0 times 2 is 0, plus 1 is 1. To get from node 1 to node 3, I multiply by 2. 1 times 2 is 2, plus 1 is 3. 1 times 2 is 2, plus 2 is 4. That's how I go down and right. When I want to go up, what I do is subtract 1 and then divide by 2. Look at how this works. 3 minus 1 is 2. 2 divided by 2 is 1. So far, so good. What about over here? 4 minus 1 is 3. 3 divided by 2 is, now I know you want to say 1.5, but it's not. 3 divided by 2 is 1, because we're in integers. So really it's 1.5 rounded down. That's what integer division does. So now I've shown you how we can navigate around a tree of this shape without needing pointers. All we need to do is do math on the array indices. All right, now let's talk about the heap part. We want to store the numbers in yellow here. We want these yellow numbers stored in what we are calling the heap property. The heap property is that a parent's value is less than or equal to its children's values. So that means that the ordering here is not the usual tree ordering where smaller things are on the left and bigger things are on the right. Instead, smaller things are on the top and bigger things are further down. And if every time we go up, the parent is smaller than the child, then the smallest thing must be the root of the tree. And since the way this tree is stored, the root is always node 0, we know that the smallest thing in the heap is always at array index 0 in our storage, which is kind of neat. All right, so we need to walk through how do we insert and how do we remove. Let's start with insert. The next available slot is, well, we go from top to bottom, from left to right. So the next available slot is there. And let's say we're inserting the number 3. It goes at position 8. The problem is we no longer satisfy the heap property. So if we look at this, we can see that 3 is less than 7. And we need to have the smaller number on top, the bigger number below. So we're going to swap them like that. Now, We satisfied the heap property for this subtree, but we need to look further up because 3 is less than 4, and we need to have the smaller numbers on top again. So we're going to swap. At this point, now we're satisfying the heap property from that 3 and everything on down. How about here? Well, 3 is not smaller than 2, so we don't need to do another swap. At this point, we're done, and we've satisfied the heap property for the entire heap. The cost? Log n. Because these trees never get unbalanced, it's always log n. It's always a logarithmic path from the bottom to the top. Stable, predictable, simple. All right, how about removing? Well, the answer is right there on top. 2 is the smallest value in this heap. So we know that that's what we're going to ultimately return. We're going to return that number 2. But we need to resatisfy this heap property. And we also have to deal with this complete tree property. So that number down here, this one, can't stay where it is because a heap with 8 entries, indices 0 through 7, cannot have something in this position. It has to move. So what we're going to do is we're going to save that number 2 on the side. That's what we're returning. And we're going to move the number 7 up there. So 7 is temporarily on top. And now, rather than working our way bottom to top, we're going to work our way top to bottom. It's a little bit confusing, but we're going to start here. And we're going to say, we need to re-establish the heap property. So we need to, 7 is not the smallest thing, so we need to move the smallest thing up. In this case, either one will do. Let's say we go left. So the 3 moves up, the 7 moves down. So we've started satisfying the heap property, but we need to keep going. So once again, we need to move the smallest thing to the top. In this case, that's the number 4. So we're going to swap the 4 and the 7. Now we're going to do one more step. Oh, the smallest thing already is on top, therefore we're done. So once again, it takes us log n work to work our way from the top to the bottom, and we know that the heap is always logarithmic because we're storing in the complete tree. So it's never worst case any worse than log n. All right, our use of arrays is a serious win. It means that we can navigate up and down just by doing integer arithmetic. We don't have to deal with all of these pointers, so we use a lot less memory, and that makes our code very efficient. As I mentioned before, these aren't just expected case log n, where the tree might get unbalanced and have some worst case behavior that's worse. Nope, because a heap is in a complete tree, it's always log n. And we don't even really have to worry about what if I have an array of one size and I need more. If we use Java's array list, it will deal with the internal reallocation and copying for us. So the code that you'll have from us next week, it uses array list to deal with the storage. Now, here are some simplistic performance numbers. This is hardly a high-tech performance benchmark, but what we did was 1,000,000 inserts followed by 10,000 fetches, and we divided the resulting time by 1,000,000. And that gives us a vague idea of the cost of doing this much work. It's not perfect, it'll do. So for our 3 different first in, first out queues, so our functional list queue is on top, and that's the one that you're implementing this week. You'll see that it takes it 82 nanoseconds per operation, whereas our Java collections classes do it in 34 or 35 nanoseconds. So that's a factor of 2.3x. That's actually kind of a big deal. So if you want that extra speed, then you might prefer the mutating interface. Whereas if the speed is less important to you and you prefer the functional semantics, then you might prefer our functional version, and it's really your choice. What about priority queues, though? So Vaver's priority queue, which I haven't told you how it works, but it's super cool, is the slowest, but it's not that much slower. Our binary heap is in the ballpark of Vaver's priority queue. The performance difference here is not the sort of thing that you would use to make a big decision about which one you want. Instead, you'll say, well, do I really need functional semantics or do I really need mutating semantics? Now, what's the difference between the Java priority queue and the Rice binary heap? Well, the answer is they're using the same underlying algorithm, but the Java priority queue was carefully hand-tuned, where over the years they have worked and tweaked and modified, and it doesn't use array list, it does its own thing. Does that mean that the Rice binary heap is no good and the Java priority heap is definitely the answer? Well, maybe, but the Rice binary heap code is written to be relatively easy to read, and you're welcome to go look at the Java code yourself. It's all available to you. But the moral of the story here is that the functional priority queue is not necessarily slow by virtue of being functional. So speed and interface don't necessarily have to be tied together. All right. Next week in lab, you will use our binary heap, which we are providing to you, to implement sorting on sequences. You're going to create a binary heap, load everything in, and then extract it back out again. So if each operation is order log n, then if you do it n times, you're going to get an n log n sorting function. And the name of this sorting function is cleverly called Heaps sort. That's actually its name. So that's lab for next week. We'll deal with that next week. What I want to talk about now, though, is that in order for you to put anything you want into this heap, you need to have a less than function. You need to have a way of determining the priorities and determining how to do those swaps. And if what we're doing is just integers, you could imagine that we build it in, but no, we want to do it in a general purpose way. We want to be able to sort in arbitrary, complicated orderings. And if I tell you to build a more complicated ordering, it's actually a lot of work, it's tedious, and it's easy to get it wrong. So we're going to talk for the rest of this lecture about how to build complicated orderings. So for starters, many Java classes, including integer, double, and string, support an interface called comparable, java.lang.comparable. And what that means is they have a method called a compare to b. And what happens is, if you say, this string dot compare to that string, if the answer is less than 0, that means that a is the smaller one. If it's greater than 0, that means that b is the smaller one. If it's equal to 0, that means they're the same. And this is built into to several of the Java classes you've been working with so far. And we're going to say that they have a, quote, natural ordering. Not every class has a natural ordering, but these ones do. So when you have a class that implements the comparable interface, we'll say that that class has a natural ordering because it has a comparison function. So while you're programming with Vavr, Vavr has its own built-in sorting function. So you have a sequence, you can say sequence.sorted in several different ways. I've simplified the interface here to make it easier for the slides. You can go look at the Vavr code to see how the actual methods work. So for starters, just like I can say sequence.map of a lambda or sequence.fold with a lambda or sequence.take20, I can say sequence.sorted. And what I will get out is a copy of the sequence in its sorted order in its natural ordering. So if that was integer, they'll be ordered from small to large numbers. If it's string, they'll be sorted alphabetically. And if it's some type that isn't comparable, this will throw an exception. It will say, I'm sorry, I can only sort things that are comparable. You gave me a sequence of things that aren't comparable. I can't sort that, and it'll throw an exception. So how can I sort things that are not comparable? So option one is that you can build a thing called a comparator. More on that in a minute. And a comparator is the thing that that's a general purpose comparison contraption. Again, more on that in a minute. But the other version is that I can build a lambda that maps from whatever the type of that object is to something else that is comparable. So for example, in week 2, we had our car manufacturers and car models. So if I want to do is sort cars based on their model name, then if I have a list of cars and I want to sort based on the model name and the method is called getName, this mapper might be x_arrow x.getName. And so even though our car models are not ordered, I've just defined an ordering by saying we're going to sort them by name. So x_arrow x.getName, and now I have a function, and now I have an ordering defined, and now I can say sort by with a lambda. Easy. Java.util.comparator, built into the Java collections classes, lets us define any ordering of any kind. So it's a general purpose way of sorting anything. So let's start with a simple challenge. I have a bunch of strings, and I want to sort them first by string length. And then if the lengths are equal, I want to sort them in alphabetical or lexicographic, those are synonyms, by an alphabetical order. And I want to do this with comparators. So I've got two different lexicographic orderings I might want. The first one would be ascending. A is before B is before C. The other one is descending. So C is before B is before A. So I've got two different desired outputs by sorting this input. The input has a series of strings. I want the shortest strings in front, so cat and dog come before lion, llama, and zebra. But since cat and dog are the same length, I might want cat to come before dog. That would be alphabetical order, or I might want opposite alphabetical order, where dog comes before cat. So here are two different comparators. The first one, much like that sort by method on the prior slide, says we're going to have a comparator that compares by length. And as long as that lambda returns a thing that's comparable, then we can build a comparator that compares based on, well, in this case, string length. Also, we can have a comparator that compares in natural order for any type that is comparable. So in this case, it's returning a seemingly uninteresting comparator that does it in the string's natural order. So far, so good. Here's where the fun happens. That we have all these operations that allow us to combine the comparators. So the first assert equals, you'll see that I'm saying sort the inputs by the string length order, then the string natural order. So string length order, and then if they're equal, then compare by the string natural order. So this then comparing method lets me combine two comparators, and it returns another comparator. If you look at the second line, you'll say it's the string length order, then the reverse of the string natural order. So I've got all these interesting operators that I can do on comparators that let me get more comparators out, and combine them, reverse them, etc. And what we're doing is called higher order functions. These methods on comparators build new comparators for us. All right, that's the end of our first lecture, and there will be a second video where we do some debugging. But I want to get this one online first, because I have a plane to go catch, and hopefully by tomorrow I'll have the debugging lecture online. Thanks.